All right, guys, welcome to the Unit 5 test study guide. I'm going to be going through all the questions this time, not just the even ones. And as usual, I would encourage you guys to do as much of this on your own as possible, and then just watch the video after the fact to check your work, okay? But that being said, we'll go ahead and begin. I'm going to go ahead and do numbers 1 and 2 here simultaneously. Number 1 is asking for the absolute max and min. Number 2 is asking for the relative maxes and mins. All right, so for number 1, the absolute max is the highest y value on the graph. Now it would have been this point here, but there's an open dot. So therefore we're going to say the absolute max actually does not exist. Absolute min is the lowest point on the graph, which to me looks like it would be right here. And we're just going to do our best to estimate the value of this point. It looks like the x value is -6 and the y value is about -12. Okay. So absolute maxes and mins are the highest and lowest y values on the graph. Now relative maxes and mins are points that are higher and or lower than any point that are immediately next to it. And more often than not, they just look like the top of a hill or the bottom of a hill. So in this case, this point right here is a relative max. So that's -3, 4. And the relative min would be this guy down here, which is 2, -7. And that's that. Pretty simple, straightforward there with those things. Just keep in mind that it's possible for your relative extrema to be the absolute max. So for instance, if I had drawn my curve to look more like this, even though there's an open dot here, now this point's higher, and so that point would be a relative max and it would be the absolute max, okay? Something else to keep in mind is that relative extrema cannot be on the endpoints, whereas absolute extrema can be. All right. So all that being said, let's go ahead and move on to question 3. Question 3 is asking us to identify the intervals where the function is increasing. Okay. So that means where the graph is moving in an upward direction. That would be here and here. In this chapter, we always move from left to right. So if I'm moving from left to right, you can see my dots are going in an upward direction here. So that would be increasing. Okay, same thing over here. And so that interval is an increasing interval. So we have 2 of them. The left one starts here. We're going to estimate that at -6. And then after that, it keeps increasing until we get to here, which is -3. So there's one interval where it's increasing. And then also it's increasing on the other yellow interval where it starts here at 2. And then it keeps increasing until we get here, and that x value is about 5. And there you have it. Now I'm going to use parentheses because it's not technically increasing at the end point. It's increasing between these points. All right. Let's go ahead and move on to number 4. Now number 4 is asking the opposite question. That is asking where is it decreasing, and that's right here. We're moving in a downward direction at that point, or in this region, I should say. So for number 4, we're decreasing on the interval from x equals -3 to x equals 2. Okay. All right, let's go ahead and move on to number 5. Identify any critical values. Okay, so just to remind you, critical values are those points where either f prime equals 0 or f prime is undefined. Okay, now f prime can be undefined in a lot of ways. One way it could be undefined is at a cusp. Another way it could be undefined is some sort of discontinuity on the graph, like a jump, a hole, or maybe an asymptote. Those are all ways that a function may fail to have a derivative at that point. Now, a place where the derivative is equal to 0, that's either like the top of a curve or the bottom of a curve. It could also be something that looks like this. So those are ways that a function can have a zero slope. So all these are places where we would find critical values. Now, I don't see any of these on the graph that we have here, but I do see the top of a curve and I do see the bottom of a curve. And so we can go ahead and say that our critical values are at x equals -3 and x equals 2. And notice I'm only going to put the x values because critical values are x values. All right, let's go ahead and move on to number 6. Number 6 says, if the point 0, -3, which we're going to guesstimate is like right about here, is a point of inflection, find the interval for which the function is concave up and concave down. Now, the reason I specified that this was the point of inflection is because that's where it switches from one form of concavity to another. So on this half of my graph, we have one form of concavity, and on this side we have another form of concavity. And so this one is asking us to identify the intervals for which the function is concave up and down. So I'm going to abbreviate here, con up and con down. Concave up is the yellow portion of our graph. So that starts at 0 and it goes on until we get to that open dot on the right side, which is about 5. Concave down is the green region, which starts at -5 and then keeps going until we get to about 0. Okay, so just want to make sure we know how to identify all the parts of a graph. All right, let's go ahead and take a look at number 7 here. Number 7 is asking us what is the EVT, and our answer should include the conditions that are necessary for the EVT to be applied to a given function. All right, so the EVT stands for the extreme value theorem, and this theorem promises us that if a function is continuous on a closed interval, there has to be an absolute max and minimum on somewhere on the interval. So no matter how you look at it, if you have a function that's continuous, it has no holes, gaps, or jumps, well, somewhere on the closed interval, meaning the endpoints have to exist, somewhere there's got to be an absolute max and a min. It doesn't really matter how you graph it. But as soon as there's a gap in the function of some kind, well, the EVT says, well, now we're not really sure it exists. So the EVT doesn't tell you where they are, it just tells you that they are. So the EVT promises that if a function is continuous and on a closed interval, there must be an absolute min and max somewhere. Now I said make sure your answer includes the conditions necessary for the EVT to be applied. And the conditions are that the function needs to be continuous and it has to be a closed interval. And all this closed interval stuff means is that just means the endpoints need to be included in the interval. Okay? In other words, the interval should be written with brackets. Okay, so if you're using open brackets, well, that means the endpoints aren't included. And now we can't be sure if there's an extreme value theorem, because if the highest point was at one of these endpoints, well, we saw on number 1 that if you have an open dot at an endpoint and that's your highest point, now you don't have a max anymore. So there you guys have it. So just to restate it, the extreme value theorem is a theorem that promises us that if a function is continuous on a closed interval, there has to be at least one absolute max and one absolute minimum on that interval somewhere. Okay, let's go ahead and take a look at number 8. Says, what is the MVT? Your answer should include the conditions that are necessary for the MVT to be applied to a given function. So the MVT stands for the mean value theorem, and this theorem promises us that if a function is continuous on the closed interval AB and differentiable on the open interval AB, there must be some value C such that f prime is equal to f of B minus f of A over B minus A. Now that probably doesn't have a whole lot of meaning to you right now. I don't know, maybe it does if you remember, but this is the instantaneous rate of change. And this formula here is the slope formula. This is y2 minus y1 over x2 minus x1, also known as the average rate of change. Now, if we have a function that, say, goes from here, a, to b, what this theorem is telling us is that so long as this is a continuous function on the closed interval, meaning the endpoints are included, and the function is differentiable, like that would mean there's no cusps or anything that would cause the derivative to fail to exist, so long as those criteria are satisfied, then the average rate of change, which is represented by the slope of a secant line, in case you forgot that, that's the average rate of change, should be equal to the instantaneous rate of change, which is like the slope of a tangent line, somewhere between a and b. So in other words, when two slopes are equal, they're parallel. So there's got to be some value of c somewhere between here where the tangent line is parallel to the secant line, or f prime is equal to this difference quotient here. All right, so that's what this theorem promises us. So the mean value theorem stands for, well, the mean value theorem promises us that if a function is continuous and on the closed interval and differentiable on the open interval, then there has to be some c in between the a and b such that the tangent line at that point is equal to the slope of the secant line between the two endpoints of that interval. Okay, and this is the formula that basically says what this picture represents. Okay, so so far we want to clarify a couple of things here, though. So why does it have to be continuous on the closed interval? Why is that? Well, that means the endpoints are included. And that's important because if the endpoints weren't included, then these points right here wouldn't exist. If there was open dots, there would be no f of a and f of b. Why does it need to be differentiable on the open interval? Because the derivative has to exist somewhere in between those dots. So long as the derivative exists everywhere between there, then there has to be at least one. Okay? And so that's why those two things are required. And those are the things that I'm referring to here when I say the MVT should, your definition should include the conditions that are necessary. So the function needs to be continuous on the closed and differentiable on the open interval. All right? And so that's the MVT. So for numbers 9 through 14, we're going to be determining whether or not the EVT and MVT can be applied to this function on the interval that they give us. Okay. Now, we're looking at various kinds of functions here, and you might want to take a look at this sheet, which, in case you haven't noticed, we use this quite frequently. So it's something you might want to have in the front of your notebook, and if you don't remember where it's in lesson 3.3 part 2. But you're going to need this sheet in order to know where functions are continuous or not. So make sure you have that out and ready to go. All right, so number 9, we want to know, does the EVT apply to this function? And we also want to know, does the MVT apply? Okay, now for the EVT to apply, the function has to be continuous on the interval AB. For the MVT to apply, that has to be true as well. It has to be continuous on the closed interval AB, but it also has to be differentiable on the open interval AB. Okay, so let's go ahead and see how this works out for us here. So this is a rational function. Rational functions have discontinuities when the denominator equals 0. And in this case, my denominator is x minus 3. And so if I solve, we find out that x equals 3 would be a discontinuity. So the next thing we have to do is we have to ask ourselves, okay, so this function does have one discontinuity. It has a discontinuity at x equals 3. The next thing we have to ask ourselves, is it on this interval? Is 3 in between 4 and 10? And the answer is no. So even though this function does have a discontinuity, it's not on the interval that we care about, and so the EVT checks out. So yes, somewhere on this interval from 4 to 10, the EVT promises us that there has to be an absolute max and an absolute min somewhere. Okay? Now let's go ahead and see if the MVT applies. Now, the MVT also requires it to be continuous on AB. So far we're good, but it also has to be differentiable. Now I'm going to do it this one time, but you're going to find that with these types of functions, you really don't need to worry about doing the derivative on these. But basically, how do you tell if it's differentiable now? That's the question. To tell if a function is differentiable, you need to find its derivative first. So this is a quotient rule. We're going to do low d high minus high d low, draw a line and square below. Now, we could simplify this. This cancels out and this is negative 5, but we really don't even have to. Why not? Well, because all that we really care about is we want to know is this differentiable on our open interval, right? Now, once again, the derivative is also a rational function. My original function was this, which is a rational function. Its derivative is also a rational function. And in fact, the denominator of this one is the exact same thing as this one. It just has a square on it. And so in order to tell if this function is differentiable, all we need to do is find the derivative and find out where the derivative is not continuous. Well, the derivative is not going to be continuous at x equals 3 also. It's the same denominator pretty much. It's just being squared. So the derivative is also discontinuous at 3. But guess what? We're still on the interval. Now, this is closed, but even if you make it open, which is what this says here, even if you make it an open interval, it's okay because this discontinuity is not on it. So it checks out. Okay? So the MVT can be applied to this function because not only is it continuous on the closed interval, but the derivative is also continuous on the closed interval, which means it's also, the derivative is also continuous on the open interval, which means that it's differentiable there. And so the MVT applies to this function as well. So the answer is yes, it applies. Okay, so that means that somewhere between 4 and 10, if you were to graph this function, it would look something like this. We don't really need to graph it, but somewhere between 4 and 10, which makes a secant line, there's going to be a slope somewhere along there that's parallel to that. That's what the MVT promises us. And the EVT promises us that somewhere between 4 and 10, there's a max point and an end point as well, a minimum point, I mean. So all that to be said, yes, the MVT and the EVT can both be applied. So what's the basic strategy here? Find out where the discontinuities of your function are, then find the derivative of that, and find out where the derivative's discontinuities are. And once you guys find both of those, you can decide, does the EVT apply or not? So let's go ahead and take a look at number 10. So once again, it's another rational function. So there's going to be a discontinuity when the denominator equals 0. And in this case, my denominator is x squared minus 4. Now, to solve this one, we're going to add 4. And you guys got to be careful here because I know a lot of you guys tend to forget to do this. But when you take a square root, you need to remember that that gives you a plus and a minus. So we actually have two discontinuities. One is at 2 and one is at negative 2. Okay? Are either one of those numbers, 2 or negative 2, are either one of those between 1 and negative 1? The answer is no. So even though this function does have discontinuities, it's not on the interval that we care about. So this function is in fact continuous on the closed interval negative 1 to 1. Now let's see, is it differentiable? Well, to do that, like I said, you find the derivative and you find out where the derivative has discontinuities. But now I'm going to save myself a little bit of time. You can still do the whole quotient rule if you want to, but I'll give you a little hint. You don't have to. All that we really care about is the fact that whatever the bottom is equal to 0 at. And as you guys know, when it comes to the quotient rule, the bottom stays the same. You just end up squaring it. And therefore, it's going to have the same discontinuities as the original function. And so therefore, it's also differentiable on the open interval. Okay? And therefore, once again, both the MVT and the EVT apply. I should have said that on number 9 as well. I shouldn't have just put yes. They both apply. Okay. Let's go ahead and take a look at number 11. On number 11, my denominator is x squared plus 9. And as you guys know, the denominator can't equal 0, right? So I'm going to set that equal to 0 and see what I get. Now this is another thing that we kind of came across. When you take a square root, sure, we can put plus and minus there, but the thing is, you can't really take the square root of a negative, right? That's an imaginary answer. And when you get an imaginary answer here, that means there are no discontinuities. So if there's no discontinuities, then guess what? It has to be continuous. In fact, it's continuous everywhere. And so because of that, we could say that both the EVT and the MVT apply. Now, notice I'm showing even less work this time. But how do I know the MVT applies? Well, because we've already proven that it's continuous on the closed interval, right, for EVT. And that's part of what we have to do for MVT. But also for MVT, we're supposed to take the derivative, right, and then find out where the denominator equals 0 then. But it's the same denominator, so it's going to be the same answer. And so there you have it. So it works for both once again. So all those it works. Let's take a look at number 12. Now this is a different function from the first 3 that we looked at. The first 3 that we looked at here in 9 through 11 were all rational functions, but this is a square root function. And so when you look at a radical function, they really don't have any discontinuities anywhere. So we don't have to really worry about that. So since there's no discontinuities, then we already know it's going to be continuous on the closed interval from 2 to 9, which means that at the very least, EVT applies. Okay, now the derivative, though, is a little bit of a different question. Is it differentiable on the open interval? That's our question now. Well, let's see. Well, to do that, this is different. We actually do need to find the derivative. How do you find the derivative of a square root function? Well, the way that you find the derivative of a square root function is you might want to change it into a half power like so. You're going to then apply the chain rule. So if this is my function, I'll call it y, then y prime is going to be multiplying the front by the half and then subtracting 1 from the power and then multiplying by the derivative of the inside. Okay, so that leaves me with y prime is equal to, the 4 here is going to stay in the numerator. This 2 here is in the denominator. And since this thing has a negative power on it, it's going to go to the denominator as well. And as you guys know, half powers are square roots. So there's my derivative. Now, if you want to go through the trouble of reducing it, you can. It's not really necessary for what we're working on right now, but there it is. So now, when you take the derivative of a radical function, it becomes kind of like a radical and a rational function because now it's got a denominator, right? And as you guys know, with rational functions, the denominator can't equal 0. So if I set this equal to 0 and solve, I'm going to find a discontinuity. And it turns out it is at 2. Now, question, is that okay? Because it's at the endpoint. And the answer is yes, it's okay for it to be have a discontinuity at the endpoint because you see the parenthesis there. That means it doesn't matter if it's included or not. So it has to be differentiable in between 9 and 2. That's what these parentheses mean. We don't include the endpoints. And so I do have a discontinuity, but it's at a point that I'm not considering anyway. I only care about the points between 9 and 2. And so once again, It is differentiable on the open interval, and therefore, yes, once again, the MVT applies. You guys are thinking, well, okay. So it looks like Mr. Bailey's just going to give us a whole bunch of questions where both of them apply. No, that's not true. I just happened to pick these kinds because I wanted to show you various things that come up along the way. So actually, number 13, I think we're going to find that one of them does not apply. Let's go ahead and see which one that is. So our first question here is, does the MVT apply? Well, let's see. This is a cube root functions. Now, cube root functions are continuous everywhere. There's no discontinuities. So yes, it is going to be continuous on any interval, and that would include the one that they're giving us. So that means that the EVT applies. There has to be an extreme value. But now, does the MVT apply? Well, we need to find the derivative. So let's do that. So y is equal to the cube root of x plus 5. To find the derivative, the first thing we're going to do is we're going to rewrite it as a power of 1/3. And then we're going to apply the chain rule. So we're going to multiply the front by 1/3. We're going to subtract 1 from that power. And then we're going to multiply by the derivative of the inside, which is just 1, so it doesn't really matter. My numerator then is going to be 1 over 3. And then on the bottom, we're also going to have x plus 5 to the 2/3 power. Okay, so where will this have discontinuities? Well, now what used to be a cube root function only has now become a cube root function, but also a rational function. And once again, rational functions can't equal 0 in the bottom. So this x plus 5 can't equal 0, and I end up with -5. So now, is -5 on the open interval from -13 to 3? It is. So this function is not differentiable on the interval -13 to 3. Okay, so how would I answer this particular question? For this one, I would say, since the function is continuous on the closed interval, -13 to 3, the EVT does in fact apply. However, since it's not differentiable on the open interval from -13 to 3, the MVT does not apply. So this is one where the EVT applies. In other words, there is some maximum and minimum value on the interval, but we can't really be certain that there is a tangent line that's parallel to the secant line somewhere on that interval. All right, so there's that. All right, let's go ahead and take a look at one more like that. And you know what? I think this is kind of overkill. I think we'll go ahead and just cancel that one out. We won't include it. Let's move on to 15. All right, so number 15, find the critical values. All right, so they give us a function here, and our job is to find the critical values. Critical values are where the derivative is either 0 or undefined. So the first thing we're going to do is we're going to find our derivative of that function. The derivative of that, using the power rule, would be 3x squared minus 4x minus 7. Now that's a polynomial, and so therefore, where will the derivative be undefined? There will be no places where the derivative is undefined, because polynomials are continuous everywhere, so therefore there won't be any discontinuities for that derivative. But we can find some places possibly where the derivative equals 0. Now, you guys can use either the quadratic formula or you can use factoring. I'll leave it up to you. I'm going to go with a factoring approach, and I'm going to set this thing equal to 0. Okay, so what times what makes 3x squared? I would say 3x times x. And what times what makes 7? I would say 7 and 1. And then we got to play with the signs a little bit to try to get this to work. I know that 1 times 7, it needs to be a -7. And I also want the middle here to come out to be negative, so I know the bigger one needs to be negative there. So there's that. And you should definitely FOIL it out to see if it works. Now, I know that mine works, so I'm not going to do that, but there it is in factored form. Then what we're going to do is we're going to set each piece equal to 0 and solve. So I end up with x equals 7/3 for that one, And for this one, I end up with x equals -1. So I've got two critical values there, and that would be the answer to number 15. All right. Let's go ahead and move on to number 16. Number 16 is asking us to find the intervals on which the function is increasing and decreasing. And to do that, you're going to, oops, let me adjust my screen here. You're going to do the number line test, and you're going to put those critical values that we found on the last problem in there. So it was 7/3 and -1, right? So 7/3 is bigger, so I'm going to put that over here, and -1 is here. It might be helpful at this point to turn this into a decimal. I noticed that some of you guys we're picking some weird numbers whenever you left it as a fraction. I would say go ahead and turn it into a decimal. 3 goes into 7 twice with 1 left over, so that's 2 1/3 or 2.3 with a bar on the top. So just kind of keep that in mind. I wouldn't use fractions here, I would use decimals. I think it'll make a little bit more sense to you guys if we do that. So don't be afraid to turn those into decimals. It will make your life a little bit easier. All right, that being said, basically, if I want to know where this function is increasing or decreasing, then I just need to pick some numbers from these three intervals and plug them into my derivative, because my derivative is a slope. And if your slope comes out positive, that means your function is increasing. If your slope comes out negative, that means your function is decreasing. So let me pick a number between -∞ and -1, so I'll pick -2. Let me pick a number between -1 and 2.3, I'll say 0. Let me pick a number bigger than 2.3, I'll say 3. And what we want to do is plug them into the derivative. Now we said the derivative earlier was 3x squared plus 4x minus 7. That was minus 4x, wasn't it? Minus 4x minus 7. Okay. Okay, so let's plug them in. So if we plug in the 2, we're going to end up getting the following. 13. And if I plug in 0, I'm going to end up getting -7. And if I plug in 3, I will get 8. Now, I don't really care about the numbers so much, but I care about the signs. This is positive, this is negative, and this is positive, which means that my function is sloping upwards here, and here it's sloping downwards, and then here it's sloping upwards again. And so my graph is going to be looking something like this, where, let me change colors here so it's easier to see. -1 is here, and this critical value is here. And as you guys can see, that's going to help us in one of our questions that are coming up soon about which ones are relative min and which ones are relative max. But for now, we're on number 16. They just want to know on which intervals is the function increasing and decreasing. So for number 16, I would say that we are increasing here, and we're also increasing here, which is this interval and this interval. And those two intervals then are -∞ to -1, as well as 2.3, or you could put 7/3 there if you wanted to, 2.3 to +∞. Okay. Also, so let's label it. This is where it's increasing. Now for decreasing, it's going to be the one in the middle here. So from here to here, we're decreasing, and therefore it's on this interval that we are decreasing. And so we're going to say from -1 to 2.3, or 7/3. So there is the answer to number 16. Now I'm going to leave all this work up here for number 17 because it's the same process. For number 17, they're asking us to identify the relative extrema. Well, this is my relative maximum, so that happens at -1, and whatever the y value is at that point. That's my relative max, because it's at the top of the curve. And my relative min is right here. That's at 2.3 bar, and the y value that goes with it there. Okay, so that's how you can do that. So those two questions actually kind of go together. Matter of fact, all three of these go together. After you find your critical values, that helps you find where it's increasing and decreasing, which also helps you find the relative extrema. Okay. Now I'm going to go ahead and actually find out what these are eventually. You'll see on the next problem that we do, but for now I'm just going to leave it like that. So let's go ahead and take a look at number 18. Number 18 asks us to find the absolute extrema. Okay, to do that one, we're going to be doing the candidates test. Now the way that the candidates test works is you're always going to include any endpoints that they give you. So on this problem, my endpoints are from -2 to 5. And you're also going to include any critical values, which we've already found as well. And by the way, I'm going to be setting your test up like this as well, so that after you've done the work for 15, it helps you do 16 and then 17 and 18. Now the key here is you guys really need to know how to find those critical values. Can you factor, use the quadratic formula effectively? If not, that's going to make these problems difficult. So make sure that you guys know how to do those things. Now the absolute extrema is going to be the highest and lowest y values. So I need to figure out what is y of -2. I need to figure out what is y of -1. I need to figure out what is y of 2.3 with a bar on the top. Or if you wanted to keep it as a fraction that we had earlier, 7/3. And we also need to figure out what is y of 5. Okay, now on this test, I would highly recommend you use a calculator for this part because that takes a lot of time to not use the calculator. So I would use it, and we talked about that back when we did this lesson, but I'll demonstrate it again for you here. So let's go ahead and pull out our calculator. All right, so the first thing we want to do is it's important to understand we're plugging it into the original function. If you want to find the y values, you plug it into the original function. So we're going to go to y equals, and we're going to type in that original function. So there's that. Now I'm going to go back to my home screen by pushing second and quit. Oops, got to do that again. All right, and then I'm going to plug the numbers -2, -1, 2.3 bar, and also 5 into my function here. So let's go ahead and push second vars, scroll over to y vars, click 1 for function, click 1 for y1, and in parentheses we're just going to put -2. So, oops, we got an error. Let's see, what did I do wrong here? I typed parentheses twice there by accident. So I'm going to type it again. Now, just so you guys know, to type something again, all you need to do is push second and then enter, and it will bring up the last thing you typed, and you just go back and replace or get rid of whatever you don't want. So there it is. So -1 is my first answer there. So I'm going to go ahead and erase this and replace it with -1. Let's go ahead and take a look at the next one here. So I'm going to push second, enter, bring up the y1 again. I'm going to replace the -2 with -1 this time. Enter. And that gives me 5. So y of -1 is 5. All right, let's go ahead and type in the next one, which is 2.3 with a bar on top, which really just means we're going to push 2.3333. So I'm just going to come in here, and I'm going to push 2.3333. I'll just put a whole bunch of 3s. The more you put, the more accurate it'll be. Oh, I don't want that 9 there, though. Let me delete that. That was an accident. So we're looking at about 13.519 for that one. Oh, it's -13.519. That's important. And then finally, we're going to do the last one, y of 5, so second entry. Now I don't want to erase all that, so I'm going to push second entry again. And what it does, instead of bringing up the last thing I typed, it brings up the one before that. It should anyway. Thought it would. I guess not. Oh well. I guess I'll just do the whole vars thing again. I don't want to type all that in again. So let's plug in 5. And I get 41 there. All right. So now we're ready to identify our absolute max. So for the absolute max, That's the point that has the highest y value, which is right here. So 5, 41 is the highest value. And as for my absolute minimum, that's the lowest value, which looks like it would be this one here. So that's 2.3 with a bar on top, followed by negative 13. And just remember, in calculus, we like to round to the thousandths place. So make sure you include 3 decimal places there. Okay. Okay, let's go ahead and move on to number 19. Number 19 asks us to identify the points of inflection. So to do that, we have our function, we have our derivative, but to find points of inflection, you need to find your second derivative. So I'm going to take the derivative of my first derivative now to get 6x minus 4. And we're going to set that equal to 0. Oops. So if we solve that, we're going to find our point of inflection. It could also be where it's undefined, but that's kind of rare. We're not going to worry about that right now. So I end up with 2/3 though. So x equals 2/3. That would be my point of inflection. Possibly. I'm not, and the reason why I say possibly is because the concavity has to change. Okay, so let's see if that actually is a point of inflection. In order for it to be a point of inflection, the concavity has to change there. So how are we going to do that? We're going to do that with a number line test. So I'm going to put my 2/3 on there. I'm going to pick a number to the left of 2/3. And so let's go with 0, and I'm going to plug that into my second derivative. Notice I'm plugging it into my second derivative because I want to look at concavity now. Then I'm going to pick a number to the right of 2/3 and plug that into my second derivative. Okay, so the second derivative we said was, wasn't it 6x minus 4, correct? So if I plug that in, if I plug 0 into this, I get negative 4, and if I plug 1 into this, I get 2. So on this interval, we're concave down. On this interval, we're concave up. And so yes, we are changing concavity between there, so this is a point of inflection. So the answer to number 19 is 2/3. Okay. Now they also want to know where's the function concave up and down. We've already done the work for that though, so for number 20, we'll just go ahead and put that on there. So we're looking for where it's concave up, and we're looking for where it's concave down. So concave up is this interval here, which is this interval, which is from 2/3 to infinity. Concave down is here, which is this interval from negative infinity to 2/3. Okay, and so that's our answer to number 20. So we've got 19 and 20. Now let's go ahead and do number 21. Number 21 is asking us, is there a value c on the interval from 0 to 1 such that y prime of c equals 0? Now, this is a mean value theorem question. Now, technically, when you do these, you're supposed to make sure it's continuous and differentiable, but I'm going to give you a polynomial for this, so you don't need to check that it will definitely work. So we just need to go ahead and get started with the problem. So to do these problems, we're going to do a couple things. We're going to have to find out what f of a is and f of b. Actually, I should probably use the letters they're giving us, right? Instead of f, we're using y. All right, my a and b in this case are 0 and 1. I would consider the first one a, and I would consider the second one b. So we're going to be plugging in 1 to our function and 0. So let's do that. So if I plug 1 into this function here, I'm going to get 1 minus 2, which is negative 1, minus 7 is negative 8, plus 1 is negative 7. And then I'm going to plug 0 into this function also, and I'm going to get 1 out of that. And then Once you have those, you're ready to go ahead and find this expression, y1 minus y0 over 1 minus 0, which is our average rate of change. So that's going to be negative 7 minus 1 over 1, which is negative 8. Next thing we want to do is we want to find our derivative. Now we've already done that. The derivative is 3x squared minus 4x minus 7. Now according to the mean value theorem, which does apply to this problem, the average rate of change should be equal to the instantaneous rate of change somewhere on the interval. So in other words, 3x squared minus 4x minus 7 should be equal to negative 8 somewhere. And so we just need to solve this equation here. So let's go ahead and do that. So notice that this is a quadratic equation, and before you can start solving those, you need them to equal 0. So the first thing we're going to do is we're going to add this 8 to the other side. And as a result, we're going to have 3x squared minus 4x plus 1 equals 0. And then from there, we're going to go ahead and solve. Once again, you could either factor or use the quadratic formula. Quadratic formula always works. Sometimes these problems don't factor, but I'm pretty sure this one will. So I'm going to go ahead and factor, but once again, you can always just use quadratic formula if you want to. So 3x, x, 1 and 1. In this case, they're both negative. All right, so solving this, there's one value, and then solving the other one. There's our two possible answers. Now we're only going to pick the answer that's on our interval. My interval is the one between 0 and 1. So which one of these numbers is between 0 and 1? It's going to be this guy. So there's my final answer. All right. Okay, let's go ahead and move on to number 22. All right. This question is asking us which one of the following represents a relative minimum, which one represents a relative maximum. And notice that I'm giving you a function value, a derivative value, and a second derivative value. For this one, we're going to be using the second derivative test. And according to the second derivative test, we have a relative max when the following occurs. F is defined, so in other words, there is a point there. F prime equals 0, and F double prime is less than 0. Okay, and so let's interpret this. We have F double prime is less than 0. That means we've got a graph that's concave down. F prime equals 0 means we are at the top of that curve, which makes it a max, but only if the point is actually there, which is a solid dot. Okay, now in the same way, we have a relative min anytime f is defined. At that point, the derivative is 0, and the second derivative is greater than 0. Greater than 0 means concave up. F prime equals 0 means that we're at the bottom of the curve where the slope is 0. And the fact that f is defined tells us that there is in fact a point there. And so that's a way to find a relative min. And this is all using the second derivative test. So let's go ahead and take a look at what we have here. So for number one, for all of these, notice that f is defined. F of 1 is 3 here, f of 1 is 3, f of 1 is 0, f of 1 is 4. So for each one of these options, the first criteria is good. So this isn't going to really be of much use to us. But let's go ahead and take a look at the next part. F prime needs to equal 0. So this one does. And this one does. So since neither one of these are equal to 0, the f prime is not equal to 0, then I know that neither one of these can be a relative max and a relative min. Now we just need to figure out which one of these is the max and which one's the min. For the one that's a max, the second derivative is less than 0. So that would be this guy. So A is the relative max. B, since my second derivative is positive, I'm sorry, d, since the second derivative is positive, that one is my relative minimum. Okay? Okay, for numbers 23 through 25, these are all optimization problems. You can tell they're optimization problems because of this part here. When it says find the largest area, or minimize something, those are what we call optimization problems. So, and I gave you guys some steps for those, so let's go ahead and begin. Step 1 is to draw a picture. So it says here a farmer wants to construct a rectangular pig pen using 100 feet of fencing. The pen will be built next to an existing stone wall so that only 3 sides of fencing need to be constructed to enclose the pen. So we have a wall. And then what's going to happen is the farmer's going to build a rectangular region like that using the fencing that he has available. On a rectangle, we know that we don't know what these sides are, but we do know that they're the same. And then we have this side over here. Okay, so there's my picture of the situation. Step 2 is to go ahead and to find your primary equation. Your primary equation is the value you're trying to maximize. I'm trying to maximize the area of this pig pen. And so how do you find the area of this rectangle? It's A equals X times Y. Okay? So the next thing we want to do is we want to find our secondary equation. And that's usually going to be the one that's limiting your possibilities. And the fact that I only have 100 feet of fencing is my limitation. And that is this stuff here, which is like the perimeter, if you will. And so that's X plus Y is equal to, should all add up to 100 feet of fencing. So I've got 2 X's and 1 Y, all adding up to give me 100 feet of fencing. So that's my limiting factor. So my primary is the one I want to maximize. My secondary is the one that limits my possibilities. And now we're ready to solve the system of equations with substitution. So when it comes to solving a system of equations, there are some steps in that process. The first one is to get a variable by itself so solve for one of the variables in your secondary equation. So my secondary equation is 2x plus y equals 100. And it doesn't really technically matter which variable you get by itself, but there is a smarter choice. If I choose to get the y by itself by moving the 2x over here like that, I don't end up with any fractions. If you tried to get the x by itself, you're going to end up with some fractions. So, make your life easier if you can. So that's the first thing that you're going to do. The next thing you're going to do is you're going to take this value here and you're going to substitute it into the other equation. So what do I mean by that? If y equals 100 minus 2x, I can replace the y in my primary equation with 100 minus 2x. So that's what I'm going to do. It's going to be a equals x times y, but instead of y now I'm going to put 100 minus 2x. Okay. From there we're going to simplify it by distributing, so let's do that. And that's going to give me 100x minus 2x squared. So now what we're going to do is we're going to find the derivative of that new equation that I just created. So there's the equation. We're going to find the derivative because that's how you find a maximum value. We're going to set that equal to 0. That's a critical value. And at critical values, that's where we often have our maxes and mins. So that's why we're setting it equal to 0 there. And I end up getting 25. And so that means x is 25. Okay. So I guess I should have put here, find derivative, make it equal to 0, and solve. Right. Now, you got to make sure, though, that the answer that you found is what they're actually asking for. The question is asking what dimensions does the farmer want to use when making the pig pen. So for that, let's go back to the picture from step 1. Our picture looks something like this, right? Well, we just found out that x is 25, right? We know we're allowed to use 100 feet of fencing. So if this is 25 and this is 25, what's left to make 100? Well, we had our formula, right? 2x plus y has to add up to make 100. You could do it this way also. Just plug in your value for x that you know and solve for y. This is 50. And then if we subtract 50 on both sides, we find out that y equals 50. So the answer is x equals 25 and y equals 50. So there's your steps. All right, let's go ahead and take a look at the next one here. A cryptography expert is deciphering a computer code. To do this, the expert needs to minimize the product of a positive rational number and a negative rational number. Given that the positive number is exactly 9 greater than the negative, what's the final product that the expert is looking for? So for these types of problems, we're going to be skipping step 1. It's not really a geometry problem, so I can't really turn this into a picture. So we'll skip step 1. Let me clear all this stuff off from the last problem. All right. So step 1 for cryptography problems, where we'll skip it. Step 2, though, we are going to go ahead and write out our primary equation. So what I'm trying to minimize here is the product of a positive rational number and a negative rational number. So the product is the positive rational number. What letter should I use for positive? I'll use S for positive, I guess. And then negative. So my product is my positive number times my negative number. I'll put signs above it just so I can remember which is which. That's my primary equation. That's the one I'm trying to minimize. Step 3, what's my limiting factor? That's going to give me my secondary equation. It tells me that my positive number is 9 greater than the negative number. So that's my limiting factor. I can't just pick any two numbers, that they have to be 9 apart. Okay, and then step 4, we're going to go ahead and do our solving of the system, our substitution method once again. Now, notice that in my secondary equation, I've already got a letter by itself. I see that S equals 9n. So I just need to plug that 9 plus n there into this equation. So P is equal to S times n, and S is equal to 9 plus n. And therefore, simplifying that, we end up with 9n plus n squared. For step 5, we want to find our derivative. And then set it equal to 0 and solve. So I minus 9 on both sides, and I get negative 9 equals 2n. And then we divide, and I get negative 9 over 2 is my n. And remember, n represented my negative number. Now the problem is asking me for what's the product. In other words, they don't want to know the negative number only. They don't want to know the positive number only. They want to know what is their product after you multiply them together. So I need to go back now and find my positive number. And once I have that, I can multiply them together to get the answer they're asking for. So my positive number, as you guys know, is 9 more than my negative number. And we just found out that my negative number is negative 9 over 2. So we want to go ahead and combine these together to get an answer. I can change this to 18 over 2, so these have a common denominator. And then I can subtract them, and I end up with 9 over 2. So I've got 9 over 2, and I've got negative 9 over 2. Finally, the question is, what is their product? So my positive number is 9 halves. My negative number is negative 9 halves. And therefore, the final product will be negative 81 over 4 is my final answer. Okay. All right, let's go ahead and take a look at one more question, number 25. This is another geometry question. It's about a rancher who's designing a corral. He wants to make 2 corrals that are right next to each other, and he's got a total of 300 feet of fencing he's going to use. And these corrals share one side. he wants to make it so they enclose the greatest possible area. So once again, on this guy, we are going to draw a picture because it's another geometry question. So we're going to draw this picture. That's two corrals that are sharing a side together like that. So I've got three vertical sides, which we'll call X's, and I've got, I'll call these little Y's here. Those four horizontal sides there are Y values. So there's our picture. Step 2, I want to maximize the area. So what is the area of this shape? The area is going to be the base times the height. Now one of these rectangles, the base is y and the height is x, so that's xy, and there's two of those rectangles, so the area is 2xy. All right. Step 3, we want to find our limiting factor. The limiting factor is we're only allowed to use 300 feet of fencing. There are 3 x values and there are 4 y values, and altogether that should add up to 300 feet of fencing. For step 4, we want to go ahead and solve the system of equations using the substitution method. And unfortunately on this one, I don't see any good way to avoid fractions. We're just going to have to deal with them here. So I'm going to go ahead and begin by I'm going to go ahead and minus the 3x, I guess, on this one. 4y equals 300 minus 3x. Let's go ahead and divide everything by 4. So we end up with y equals 300 minus 3x over 4. That's what we're going to plug in for y into our primary equation. So now my primary equation is going to look like this. 2x parentheses 300 minus 3x over 4. Let's go ahead and distribute this 2x here into the top. That's going to give me 600x minus 6x squared all over 4. So there's my new function. We're ready to go ahead and move into the next step, which is to find the derivative, it's to find the derivative of this thing. It might be good to split this up into two separate fractions at this point before I find my derivative. So 600 over 4 x minus 6 over 4 x squared. And we might as well reduce this too. 4 is going to go into 6150. And this is going to be 3 over 2 x squared. All right, so now we're good to find our derivative. That's going to be 150 minus. If I multiply this by 2, I'm just left with negative 3. It cancels out the 2 on the bottom. And the power becomes 1. Then we're going to set this equal to 0. And we're going to solve. And I end up with 50. So x ends up being 50. So once again, we want to make sure we're answering the questions they asked for, though. They're asking us for what dimensions are there. In other words, what's the length and width of these corrals? So to do that, we want to remember that we had 3 x's and 4 y's for a total of 300 feet of fencing. We just found out that the x lengths are 50, so we can go ahead and plug that in. That's 150. Minusing 150 on both sides. Get that. And divided by 4, we get that. I think that can be reduced. Y is equal to 150 over 4. I know 2 goes into the top 75 times and the bottom twice, so that means that y is going to be 75 over 2. And so there are the dimensions. The height was 50, and the length was 75 over 2. All right, so for the last problems, we're going to be comparing the graphs of f, f prime, and f double prime. For the first one, we're going to turn a graph of f into the first derivative. For the next one, we're going to turn a graph of f into the second derivative. For the next one, we're going to turn a derivative graph into the original, so it's like the reverse process of the first one we're doing. After that, there's another one like that. Number 30, we're going to turn a second derivative into the original graph, and there's two of those. So what's important to realize is that f prime is the slope of this graph. Okay, so when it comes to these, I always like to start off by looking for where the slope is equal to 0 on the graph of f. So that would be like here, anywhere you've got a horizontal tangent line. And therefore, the derivative graph will be touching the x-axis at x equals 0. And the next thing you'll notice is that on the left side of that point, f is decreasing, which means that on the graph of f prime, it will be below the x-axis to the left of that point. And then to the right of that point, f is increasing, and therefore to the right of this point on the graph of f prime, it will be above the x-axis. And so that is our answer to number 26. Let's go ahead and take a look at 27. Right, so for number 27, once again, we're going to look for those zero slopes. So we have a zero slope here at 2, so my derivative graph is going to touch the x-axis at 0. I have another zero slope here at -2, so on my derivative graph, it's going to touch the x-axis at -2. You'll also notice that this graph is getting flat over here, and that means that the slope on the left side of my graph is going to be at 0 as well. So I'm going to draw a flat line at 0. Same thing over here, flat line here means that the slope is 0 on the left side as well. Now we need to figure out how to connect these pieces together, and we can do that just by looking at this graph and asking yourself what's going on with the slope. From here to here, the slope is negative, which means that on my derivative graph, it has to be below the x-axis as I connect this arrow to this dot. So it's got to dip below and come back up like that. And then on this interval from here to here, it's a positive slope. And therefore, on my derivative graph, it's going to be above the x-axis as I connect those dots. And then finally, the last section here, we're got a negative slope again here. So as I connect those dots, it's going to be below the x-axis again, like so. And there's my first derivative. And I just realized, though, that this problem actually wants us to find the second derivative, but that's okay because you have to do this in order to find your second derivative. So let's do it. All right, so that there is my first derivative, but I do want to sketch a second derivative. So let me move this over a little bit here. I guess I'll put it down here because my final answer is supposed to be, well, it didn't go the way I wanted to. Just a second. I think on second thought, I'll just go ahead and leave it here, and I'll just make a new graph for f prime, so I'll cross that off so we know that one's not f double prime. All right, so for this new graph, my f prime, it has, to get to my second derivative, that's the slope of this one. So the slope of f prime is 0 at -4, so we'll estimate that to be about here. So it's going to touch the x-axis at -4. It also looks like I've got my zero slope somewhere between 4 and 5. It's not precise, and it doesn't really matter. But we've got another zero slope here somewhere on the right side between 4 and 5. And then I've got another zero slope up here. And so we've got another one dot here. So for these 3 zero slopes on this graph, it will touch the x-axis 3 times on my f double prime graph. And once again, these are zero slopes on the left and right. Therefore, this graph is going to have flat slopes on the left and right as well. And so once again, we just need to figure out how to connect these dots. And so from here to here, it's decreasing, which means that as I attempt to connect this arrow to this dot, it's got to be below the x-axis. And from there, you can kind of just follow the pattern. It's got to go up, and then flat. Could go a little higher. I don't know how high up it goes, but it does get flat eventually. So we would be looking for a graph that looks roughly something like that. Okay, let's go ahead and take a look at number 28 now. 28 is the reverse of 26. In other words, this graph is the slope of that graph that we're trying to find. So what do we see here? I see that this derivative graph is touching the x-axis at about 0.5 and at 2. And what that means is that my f function is going to have a relative min or a relative max at those points. I also see that my derivative graph is below the x-axis until that point, and also after that point, but it's above the x-axis on this interval here. So what does that tell us? Well, if my derivative graph is below the x-axis from here up to that point, that means on this graph it's going to be decreasing until I get to that point, which is about negative 0.5. So my graph is going to be going down, 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 until I get to about x equals 0.5. Now you might have drawn yours up here. That's fine. It doesn't matter. The point is the graph is going in a downward direction until it gets to about x equals 0.5. After that, the graph is above the x-axis, right? And so until I get to 2, my graph is going to start increasing. So now it's going to start going in an upward direction until I get to, I want to make that look a little bit better. It's going to go in an upward direction until I get to 2. And then after that, once again, it's decreasing again because it's below the x-axis. So there's that. Now, it's not going to really be a cusp. It's really going to connect smoothly. So what's going to happen is it's going to look something like this, basically. Now, this could look different in a lot of ways. It could look like this. But so long as the shape is roughly changing direction at 0.5 and at 2, from decreasing to increasing, you're in good shape. All right, let's go ahead and take a look at this one here. Now this graph here has got some asymptotes on it. It's got a horizontal asymptote on the left and the right. And it also has vertical asymptotes. It has one going down this line here. And it has another one going down this line here. Now, as we saw when we were going from F to F prime, whatever asymptotes F has, F prime has them. So the same thing is true when you work backwards. If there's asymptotes on F prime, then those will also be here on F. So I'm still going to have an asymptote here for my graph of F. And we're also going to have one here at +1 also. And also the horizontal asymptotes will be the same. So we'll have end behavior where it gets flat on these ends. So that's what we know so far. Now, what else do we see here? I see that this portion of my graph is increasing, right? So I've got a positive slope there. Well, let me rephrase that. Since this line is above the x-axis, that means that f prime is positive. And if f prime is positive, that means f is increasing. Now, there's only two ways to draw this graph here. I could draw it like this, or I could draw it like this to stay true to these asymptotes. Which piece is increasing? Is this one increasing, or is this one? Well, it's the first one I drew. So I know that the left portion of my graph is going to look like this. All right. Let's go ahead and move on to the next part. All right. Now for this middle piece, you'll notice that from here to here, my derivative is above the x-axis, which means that it is f will be increasing on that interval. So what would increasing look like? Would it look like this? Or would it look like this? Hopefully you know it's this one. This is increasing. And another way that I've described how to do these problems is that whatever the graph is to the left, it stays the same. So like for instance, this line looks a lot like this line. And whatever it is to the right, it gets flipped. So this one's up here, so it gets flipped down here. That's another way I've described it. You'll notice that the derivative is below the x-axis after 0, which means that on my graph over here, it needs to be decreasing after that. Excuse me. So, decreasing, will that look like this? Or will that look like this? Hopefully you know it's this one. All right. Then lastly, we have this last portion here. You'll notice that my derivative here is below the x-axis, which means that if my derivative is below the x-axis, that means it's negative, which means on this graph it should be decreasing. So what would be decreasing here? Would it be this? Or would it be this? Hopefully you know it's the first one I drew, so it looks like this. So this is my original F graph here, okay? But instead of thinking about increasing and decreasing, you can also just kind of go with the general principle that I shared with you guys before, which is that anything to the left of an asymptote stays the same. Anything to the right of an asymptote gets flipped. And that pattern just kind of holds. So however you'd like to do it is fine. Let's go ahead and take a look at number 30. So number 30, they're giving me a graph of f double prime, and they're asking me to draw a graph of f. Now, with these, you're really working with very limited information, so you're just taking a real rough guess. Here we have a positive second derivative, and it's constant. So this second derivative is always positive, which means that if f double prime is always positive, that means f is always concave up. So this has got to be like a parabola of some kind. We don't know what the parabola looks like. It could be up here, could be here, it could be way over here. We don't know. All we know is that since f prime is always positive, f is always a concave up, which the only graph that does that is going to be a parabola. So let's go ahead and take a look at the next one here. Now, on this one, f double prime is negative from here to here, which means that on my graph of f is going to be concave down until I get to 0, so it'll look something like this. And then after that, f prime is positive, and therefore after that, after 0, f is going to start being concave up. So that would be our graph there for that one. All right, and that does it for our study guide. A lot there. Hope it was helpful, and we'll see you guys for your test. Have a good one.